So when we were talking about halogens and their ability to do SN1 and E1 reactions, remember they were tied together. But here now that we're using alcohols as our starting material or our reactant, we don't really get that connection between the two. So under some conditions we'll get an SN1 mechanism, other conditions we'll get an E1 mechanism. So in the last video where we looked at the reaction of an alcohol with HCl, we almost exclusively got an SN1 reaction. Here now, by changing something or changing the acid really, we are actually going to favor the E1 mechanism. So we still are going to have the same problem in that our OH is not a good leaving group, and we are going to use a strong acid to actually do this reaction. But the difference here is we are using a strong acid that's going to form a very poor nucleophile. Because of that, we're not going to get a substitution reaction. Because of that, we're going to get an elimination reaction. So that's the big difference. In the last reaction we were looking at, we used HCl. We probably could use HBr for that reaction. But here we're using two other strong acids, sulfuric and phosphoric acid. And the difference here is once we deprotonate these, they make very poor nucleophiles. And because of that, the only way this reaction can continue is through an E1 mechanism. So overall, what we're going to do is convert our alcohols into an alkene. And this reaction is formally called a dehydration. And we can see that because we are going to be kicking out our OH in the form of water. So they tend to call this reaction a dehydration because we remove water and then we form a double bond. So in this case, when we use sulfuric acid and phosphoric acid, our favored products is going to be in E1 reaction. So what acid you use has a big effect on the products of the reaction. So here it's still the same basic steps that you do to go from reactant to product that we had for our other elimination reactions. We kick out a leaving group, we kick out an adjacent hydrogen, and then we draw a double bond across here. So that hasn't changed. The only thing that's changed is what's our leaving group and the fact that we don't get a mix between SN1 and E1. Here we exclusively get SN1. Or excuse me, we exclusively get E1. And this has to do with what acid we're using. So the same deal, this is still going to follow an E1 mechanism. So don't try to think about it as being distinctly different. All it's going to have is an extra step where we do the protonation. So we already understand that OH is not a good leaving group. Here, to do an elimination reaction, we need a good leaving group. So the first step of our mechanism is going to be protonation, just like before. And now this H plus is coming from either sulfuric acid or phosphoric acid. Still the same basic idea. Our oxygen has lone pair electrons, so it can be protonated. The lone pair electrons are attacking the H plus from our acid, and then we end up forming this protonated alcohol. And in doing this, now it becomes a good leaving group. In the next step, same thing, just like an E1 mechanism, the next thing we do is kick off our leaving group, which in this case is water. So we break the carbon-oxygen bond, form a carbocation, and the electrons get pushed onto oxygen, so we end up forming water. So remember, during the protonation of the alcohol, we end up making the OH a good leaving group. So now the difference here is when we go to the next step, our counterion of our strong acids, in this case, sulfuric and phosphoric acids, are not good nucleophiles. So there is no nucleophile to come in and attack this carbocation. In the previous reaction, the counterion that we made, so after we had HCl, after we lost a hydrogen, we ended up making chloride, Cl minus. That's a good nucleophile. And so that went in and attacked the carbocation. Here we don't have a good nucleophile, so we don't get a substitution reaction. What actually happens is remove a hydrogen and form the double bond. That's the most efficient reaction. So in this case, the most basic thing that we have floating around is water, and we do fundamentally a deprotonation reaction. In this case, our water is acting as a base. It's going to grab a hydrogen, and in doing that, it's going to form our alkene. So the lone pair electrons from our oxygen attacks the hydrogen. Lone pair electrons attacking an atom forms a bond, so we gain a hydrogen. So we go from H2O to H3O plus. These electrons between our carbon and hydrogen bond move down and form a double bond. So a bond attacking another bond forms a double bond in this case. Same deal, electrons are leaving the oxygen. Here it's neutral, so it will become positively charged. And then here electrons are moving towards this carbon, so it goes from a positive charge to a neutral charge. So just remember, this is an E1 mechanism, but with an extra step, with the protonation. The first step involves some acid protonating the alcohol. And then step 2 and step 3 are exactly the same mechanistic steps that we had for our elimination reactions. So this here is fundamentally what happens. Don't try to think about it as being distinctly different.